So the video from last week, which I recorded on Zoom, should now be on the YouTube channel. If it's not, please complain. I, too, like to sit in my pajamas and watch mathematics on YouTube at double time. Okay, which is, I hope, what people are doing, given that hardly anyone comes now for the live lecture. So in a few weeks, I'll post the take-home midterm. So today, we'll start talking less about general categories and more about things specific to linear situations in homological algebra. So we're going to talk about complexes and exactness. We're going to focus today on a category of modules over a ring. At some point, maybe next week, we'll talk about sheaves of abelian groups. This is another context in which this all makes sense, but this is a bit more elementary and concrete. So today we're going to work with some unital ring R and its category of R modules and complexes of R modules. If you just want complexes of abelian groups, then take R to be the integers. So such a thing looks like a sequence of modules with R linear maps between them. The composite of any two in a row is 0. So the di are R linear, and let's say di plus 1 di is 0. And in particular, this means that the kernel of di contains the image of di plus 1, since the composite is 0. And by definition, the ith homology of a complex so I'll write hi of m dot to emphasize m as a sequence of modules with these differentials. This is, by definition, kernel of di modulo image of di plus 1. And there's traditional notation and names for these kernels and images. Ker di is what are called zi of the complex. These are the I cycles. The Z is because this comes from German, and there they're called cycles. And BI is image of di plus 1. These are called the I boundaries. And the language comes from topology. If you do this in singular homology, these are, say, for 1 cycles, it's a sequence of paths in your space which all add up to a cycle. And these are the boundaries. These would be boundaries of 2 simplices inside your space and formal sums of those. Okay? And taking homology is natural in maps of complexes. So given a map of complexes, so remember what a map of complexes looks like. It's a map in each degree which commutes with differentials. So fi followed by the differential on n is the same as going around the other square, so differential on m followed by the corresponding map fi minus 1. So given a map of complexes like this, you get induced maps of cycles So if I have a cycle, an I cycle, an m, and I apply fi to it, and then I apply the differential, that would be the same as applying the differential, which would kill the cycle, and then applying fi minus 1. Okay? So, so I cycles of m map to I cycles of n. And similarly, for boundaries. Because suppose I have a boundary, so that's d of something in m, and then I apply f, that will be the same as applying f and then applying d. So f of a boundary will be the boundary of f. And from this, you get induced maps in homology for every I. And it's easy to check that this is natural in maps of complexes. So if I write ch for chain complexes of R modules, taking homology, ith homology of a chain complex of R modules is a functor. So this is an easy check. It's a functor in an obvious way with these induced maps. Okay, and now we have a bunch of definitions related to these notions. So given a complex is called exact at I if the kernel equals the image. So kernel of di, let me write it like this. So the cycles, which by definition is the kernel, I know that that contains the image if the image is actually everything. So those are the boundaries. So I always have this inclusion. If this is an equality, we call it exact at I. And this happens if and only if the ith homology is 0. Okay, so that may or may not happen. It depends on the complex. And we say a complex of the form LMN. So this sequence appears often enough that we use its own special notation. You have 3 modules, 2 maps between them, which compose to 0, with zeros on the end, and you could complete it to a complex by putting zeros everywhere else. So a complex like this is called short exact, called a short exact sequence. So let me say it like this. An exact complex, so it should be exact everywhere, of this form, meaning it has 3 possibly non-zero terms, and then beyond that it's 0. This is called a short exact sequence. And it also happens sometimes that you have a complex like this, but it's only exact in this range or in that range. So if exact everywhere, except maybe at n, then it's called left exact. And if it's exact everywhere except maybe at L, it's called right exact. Okay, so let's maybe give a few examples. So given an integer, or more generally an element of a domain, in a commutative domain, let's say, or f and a non-zero divisor. It doesn't have to be a domain. Then there's a short exact sequence of the following form. I can multiply by n. The image is just the multiples of n. So if I take the quotient, that will be z mod n. So this is a surjection. And because n is not a zero divisor, the kernel is 0. Okay? So this is a short exact sequence. It's a typical kind of short exact sequence. More generally, I could have put a and a here and a mod f, so long as f is a non-zero divisor. But what if f was a zero divisor? So let's consider another example. Let's suppose, for instance, I put here, so on the other hand, if I put here z mod 4 and z mod 4, and I consider multiplication by 2. That has a kernel, right? And it has a co-kernel. So the co-kernel, if I reduce this mod 2, the kernel of this reduction mod 2 is the image of this map. Okay, so this is right exact, but not left exact. And we'll see many more examples also on the other side. So it's not left exact because there's a kernel of this last map. So if I tried to put a 0 on here, I could put a 0 on there to make a complex, but then it won't be exact right here. Okay? And so any questions about these notions? Homology, its naturality, exactness. Who has seen this before? Yeah. So let me give a few more definitions related to this. So if I'm given a map of complexes, a map of complexes is called, well, I could ask for it to be an isomorphism. That would just mean each of these maps fi was an isomorphism. This is very strong. Okay, it can happen, but it's the following thing happens much more often and is a more useful notion. So a map of complexes is a quasi-isomorphism. And we'll abbreviate that to a quism often. if the map in homology is an isomorphism. In every degree. So this is for all I. So you may have seen something similar if you know a bit of homotopy theory. In homotopy theory, a map of topological spaces is called a weak equivalence or a pi star equivalence if it induces an isomorphism in all homotopy groups of all degrees for all base points. Okay, so this is kind of a linear version of that. Okay, so this is weaker than isomorphism, and it's also weaker than a certain notion of homotopy equivalence. So this is one notion. Let me give an example. So stupid example. A complex M is exact. So remember, exact just means all the homology groups are 0. So every cycle is a boundary. So complex is exact if and only if the map from the 0 complex, where there's zeros everywhere. So there's, of course, a map to M. That induces a map on homology. If M is exact, the map's from 0 to 0 isomorphism. So this is a quasi-isomorphism. And similarly for the map the other way. So that's a stupid example. There's for people who know a bit about differential forms, if you haven't learned so much about differential forms yet, don't worry about it, but this is a very important example. So if M is, say, a C infinity manifold, then there's a complex of differential forms, so the de Rham complex. Its terms are the 0 forms, so that's the smooth functions. I should write it this way. Given a 0 form, I can take its de Rham differential. Given a 1 form, I can take its de Rham differential and so on. That goes up to the top dimension of the manifold. Here, such a thing locally in coordinates would look like a sum of functions times coordinate differential forms, and this would go to de Rham differential of fi, wedge de Rham differential of xi, and so on. So this is the so-called de Rham complex. It's indexed with upper indices instead of lower indices, and the differential increases the degree. So that's just a convention. We call this a co-chain complex, and we call its homology cohomology. So H minus I of this de Rham complex. So this is the negative region of a complex, the positive region of a cochain complex. This is called the ith de Rham cohomology. It's the closed I-forms modulo the exact ones. Those that are killed by the differential modulo those that are in the image. And the Poincare lemma, which was one of the basic things you prove about differential forms, says that on sufficiently small open subsets of M, the de Rham complex is exact. So on open subsets of M, this de Rham complex, so let me put a dr here to emphasize. This is exact except at 0. Okay. And there's a kernel. What is the kernel? The differential of a smooth function so if the open set is, no, it doesn't matter. So you know from calculus that a function has its differential is 0 if and only if it's locally constant. Okay. So if I do this on sufficiently small, say, connected open sets, then the kernel here is just constant functions, so it's just a copy of the real numbers. And then I can make a very simple complex, which is just R in degree 0, zeros elsewhere. I can include that into A0 as the constant functions. Their differential is 0, so this commutes. And this will be a quasi-isomorphism on sufficiently small open sets. On connected open sets. Okay, so we'll probably return to this example when we talk more about sheaves. But that's another important quasi-isomorphism. And this can be used, it's maybe not obvious right away, but this can be used to show that de Rham cohomology, which is something that you compute in terms of calculus, is actually computing something topological about the space M. So this implies that not obviously, but this implies that the singular cohomology, which is the dual of the singular homology we've been talking about, with coefficients in R, is isomorphic to this de Rham cohomology. So the right-hand side is calculus, the left-hand side is topology. And the fact that this is a quasi-isomorphism ends up implying this, that the de Rham cohomology, which a priori is analytic, a posteriori is actually just topological. Okay, so that's a very important example. You can take that as motivation for the notion of quasi-isomorphism. So any questions about this notion? Okay. So here's a bit of a stronger notion, which is useful in practice when it works. So first, let's see, definition. Given two maps of complexes, let's call them F and G. A homotopy between them is the following. So it's a bunch of data. In each degree, I asked for a degree-raising linear map. So you may or may not require this to be R-linear. It depends on the context. So I'm not going to specify it at the moment. So there's a map SI. It's at least additive. Maybe it's R-linear from here to here. And a map SI minus 1 from here to here, and so on in every degree, such that, so here in the vertical direction, I'm going to compare f and g. I take their difference. Fi minus gi in every degree. And so on. So a homotopy between them is maps. So Si from Mi to Ni plus 1. Such that the difference in the middle is the sum of the two ways to get from Mi to Ni using these homotopies in the differentials. Okay, so such that this difference, Fi minus Gi, is, so what can I do? I can do Si and then Di plus 1. Or I could do Dim and then Si minus 1. Okay? So I want this for all I. So that's the notion of a homotopy between Fi and Gi. The language comes from topology. If this complex was, say, a singular homology complex of a space, and this was singular homology complex of another space, and F and G were both given by continuous maps, then if those continuous maps were homotopic in the usual sense of topology, then it would follow that I could construct these homotopies. These would be coming from when you take the product with the interval in the homotopy, it raises the degree. So we'll elaborate on that probably in the exercises, but that's where the language comes from. And a special case of this is if, let me say this. You can check that homotopy is an equivalence relation on maps between complexes and a map which is homotopic to 0 is called null homotopic. So the specific homotopy would be called a null homotopy. Okay, so here's a little lemma. Let me give one more definition. The next definition would be that of a homotopy equivalence. So a map of complexes F dot is a homotopy equivalence if it has a homotopy inverse. So there's a map back the other way. So let me draw them. This is my map in this direction. This is my map back. So if there exists a map back together with, so I can take two composites. I can first apply F, then G. That will give a map from M to itself. And I want to make that homotopic to the identity, just like I would for homotopy equivalence of spaces. And similarly in the other direction. So together with homotopies for both composites. So this would be for the identity map from the complex to itself. And in the other direction, it would be for the identity like this. Okay, so this we will see in just a moment. This will imply that a homotopy equivalence is a quasi-isomorphism, but it's a stronger notion. So we will study the situations in which being a quasi-isomorphism implies a homotopy equivalence, but it's not true in general. So here's a lemma saying how all of this is related to homology. So this is the important fact from which everything else follows. So if a map of complexes is null homotopic, the map in homology that it induces is 0. And from this, it will immediately follow that if two maps are homotopic, they induce the same map in homology. Because what did it mean for two maps to be homotopic? It meant their difference was homotopic to 0. And so the difference between the maps in homology is 0, so they give the same map. So if two maps are homotopic, then they induce the same map in homology. And finally, if F is a homotopy equivalence, it has a homotopy inverse. Okay? And the composite is homotopic to the identity, therefore it gives the identity map in homology in both directions. So the map in homology must be an isomorphism because it has an inverse. Okay, so if F a homotopy equivalence, then it's a quasi-isomorphism, but not conversely. There are situations in which you have some quasi-isomorphism, but it's not a homotopy equivalence. Maybe it will be an exercise to give such an example. So I'll just prove A, which is easy, because I explained aloud how to get from that B and C. So proof of A. So suppose F is null homotopic. So there exists SIs like this, such that what? So Fi is Si di plus 1 plus di Si minus 1. Okay. What is the induced map on homology? I choose a representative for a homology class. That's a cycle. So given a cycle, I apply Fi, it maps to some cycle in N. And I claim that that is 0 in homology, which means it's a boundary. So let's just compute using this. So according to this, it's di plus 1 si mi plus si minus 1 di of mi. But it was a cycle, so this term is 0. And this is a boundary. So the image of this is 0 in homology because it lies in the thing that we factored out. Okay, very good. So that's enough of the elementary notions and definitions. Are there any questions about this? No? Okay, so now we're going to do something a little more interesting. So we want to study not just short exact sequences of modules, but short exact sequences of complexes. What does that mean? What would it mean for it to be really a homotopy? This is the definition. In algebra, this is the definition. There's another statement, which is if you start in topology with a homotopy between two continuous maps, then the induced maps in singular chains are homotopic in this sense. And that requires a little proof, but it's proved in every topology book. They come from, in the definition of homotopy of a map of continuous maps, you have x to y, you take x and you cross it with the interval. And if you look at what chains on the interval look like, there are two interesting ones. Well, three. There are two of degree 0 at either endpoint of the interval, and there's one that crosses the whole interval. And it's that thing of degree 1 in the interval which is producing this. So we'll have some exercises about this. But for now, take this as the definition in algebra. And then you could ask about the etymology of it. Why do we call it homotopy? And there will be an exercise about this. OK. So very important lemma now. Sometimes lemmas are more important than theorems, and this is probably the most important fact in homological algebra. So lemma, so it's called the Snake Lemma. So the situation is the following. So suppose we have a commutative diagram of modules. So we'll have L, M, and N. And this will be right exact. I'll spell that out in a second. And then that will map to some other complex. I'll call it L primes, F prime, G prime. Commuting means if I go this way around the square, this way is the same, and similarly for the second square. So if I have a commutative diagram of modules and maps between them, where this in which the top row is right exact I'm going to need to draw more. I'm not done drawing on this diagram, in which top row is right exact and the bottom row is left exact. In particular, this map is an inclusion and this map is a surjection. Then, from this, we get a longer exact sequence. Then, there's an exact sequence. So it starts with, I can take kernel of alpha. So if I have something in kernel of alpha, I apply alpha, it goes to 0. And so if I apply f prime, it still goes to 0. And so if I go around this way, I apply f, maybe it doesn't go to 0, but because this square commutes, when I apply beta, it does. So everything in the kernel of alpha maps to something in the kernel of beta. And similarly, something in the kernel of beta will map to something in the kernel of gamma. So they're obvious maps from kernel of alpha to kernel of beta to kernel of gamma. Okay? And likewise, if I have something in the co-kernel of alpha, it will map to something in the co-kernel of beta and map to something in the co-kernel of gamma. So they're obvious maps like this. It's also easy to see that the composite of any two is 0, just because they were induced by maps whose composite were 0. And the interesting part is that there's some additional map here called delta. I have to tell you what it is. This is why it's called the Snake Lemma, because of this map. So there's an exact sequence like this. There's some map like this where delta can be computed as follows. So it can be computed. Let me see. Let me just tell you what delta of n is. So I choose, because the map from m to n is a surjection, I choose a lift of n to m. Then I apply beta. I will check that beta is in the image of this, and then I take its image modulo kernel of alpha. So this will be in co-kernel of alpha, okay, where n tilde maps to n. And I can do that because the map from m to n is surjective. Okay. So there are a few assertions here. One is that this map is well defined. The other is that it's exact at here, 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 and here. Exactness here, 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 and here are easy to check. I'm going to let you do this. I'm going to show you why this is well defined, and I'm going to check exactness here and here. Sorry. Yeah, so exactness here and here are easy. I will check them here. So we will check that delta is well defined. and we have exactness. Kernel gamma and co-kernel alpha. Okay? So let me spell out more this construction. Okay, so choose. So the first thing I'll do is show you that this beta of n tilde is really in the image of f prime. So choose a lift of n, lift n tilde of n. So g of n tilde equals n. Then let's consider beta of n tilde. Because this right-hand square commutes, if I apply g prime to it, it would be the same as if I went g and then gamma, but n was in the kernel of gamma. Okay. So g prime of beta is the same as g of gamma, which is the same as gamma of n, which is 0 for n in the kernel of gamma. Okay. And then, because I assumed that this bottom row is exact, the kernel of gamma prime is the image of f prime, but f prime is injective by exactness. So then, since the bottom row is left exact, there's unique L prime such that f prime of L prime equals beta of n tilde. Okay? And so it makes sense to consider the reduction modulo the image of alpha. There's still something to check, which is I made a choice. I chose a lift. And so I should check that this doesn't depend on the choice of lift. But how many lifts are there? Well, any two lifts differ by something in the kernel of the map G. Okay, so we claim this is independent of choice of lift. Well, any other lift is of the form n tilde plus something in the image of f. So say f of L. But then if I apply beta to that, this will be beta of f of L, which, since this left-hand square commutes, will be beta of n tilde plus alpha of L. And f prime is injective. Okay? And then the term alpha of L vanishes in the co-kernel of alpha. So that's why this map delta is well defined. You can check that it is linear because, well, all of the maps that we applied are linear. We need to check now exactness here and here. And fact, maybe we'll only check one. So that we have time to do the next step. Okay, so let's check exactness at kernel of gamma. So what do we need to know? If I have an element of the kernel of gamma and I apply delta and it becomes 0, I want to know that it's in the image of this map. It's clear that the composite is 0, so the image is contained in the kernel. Why is that clear, by the way? Suppose I had something in the kernel of beta, and I apply this map to get something in the kernel of gamma. Well, it is its own lift, right? So it's in the kernel of beta. When I apply beta, it will go to 0. So around this way, it will also go to 0. So it will be in the kernel. But to compute the image of this, I choose that lift, which maps to 0 under beta. Okay, so check exactness at Ker gamma. So suppose n is in the kernel of gamma, and delta of n equals 0. And I want to show that there's something in the kernel of beta which maps to it under G. But what does this mean? Then this means there's a lift n tilde. So far we only know it's in M, and we want to see it's in kernel of beta. Or that there exists a lift that's in the kernel of beta. We might have to modify it a bit. So there's a lift like this, such that, let's see, beta of n tilde equals, so what does it mean for it to become 0 modulo the image of alpha? It means that up to applying this injection, it's in the image of f prime. So that's what it means for delta of n to be 0. And now let's consider this L. So it might not be the case that beta of n tilde itself is 0, but we can modify it now using L. So maybe n tilde, beta of n tilde, is not 0. Maybe we made a bad choice of lift, but now we're going to modify it. So consider the following. Consider n tilde minus f of L. This is also a lift. This is also a lift of n. Because if I apply g to this, I get g of n tilde, and g applied to f is 0. So this is also a lift of n. And now beta of this is 0. Where did it go? Where did it go? From this relation. So this n tilde minus f of L is in kernel of beta, and it maps to n. Okay? So the image of the kernel of beta surjects onto the kernel of delta. Okay. And checking exactness here is even easier. You don't even have to modify it. It's more straightforward. So let me just let you do that. So all the other things that need to be verified at claim are easy to verify, and you should do it. However, I should warn you, when I first learned the Snake Lemma, I spent a very long time verifying it. And it's one of those things that's somehow so easy it can be difficult until you get used to it. So you just have to learn to keep track of all of the choices in your head and check that everything is independent of choices. So it's an exercise worth doing to verify the rest of the lemma. We did the hard part. OK, so this is the very important lemma, the Snake Lemma. And we'll use it a lot, but the most important way it gets used is the following. Right, so let's say construction. Construction proposition. So given a short exact sequence of complexes, which means it's a sequence of complexes which in each degree is short exact. Sequence of complexes. So I'm going to write it out. So there's a map of complexes from L dot to M dot, and then another one from M dot to N dot. So short exact will mean that the induced map in each degree, the induced sequence in each degree is short exact. This is short exact for all I. So given a short exact sequence of complexes like this, there is a long exact sequence in homology. So we know that a map of complexes induces a map of in homology in every degree. And we know that it's natural. So I'll have hi of L mapping to hi of M, mapping to hi of N dot. Those are the obvious maps. So part of the assertion is that this will be exact here. And this is easy to check. Then there will be a connecting map. And we'll use the Snake Lemma to produce it. So it continues like this. And this has a connecting map incoming from the degree above, and so on. Okay, so there's connecting maps like this. All the other maps are just the maps induced by F or by G. And the assertion is that it's exact everywhere. And let me give an example. Let me give two examples. Two examples. So notice here, this map from Li to Mi is an injection for every I. So this L dot is a subcomplex of M dot in an obvious sense. We've already seen situations of subcomplexes in the seminar. So if X dot was a simplicial set, then we associated to that two complexes of abelian groups. So one of them was just, we took, in each degree, we took the free abelian group on the 0 simplices, on the 1 simplices, and so on. And these maps, these differentials, were the alternating sum of face maps. Okay. And then we also had inside of there a subcomplex of degenerate simplices. So this was degenerate simplices, so linear combinations of degenerate simplices, and that is preserved under the differential, forms a subcomplex. And then by definition, the reduced or normalized, maybe normalized, this is the normalized complex of the simplicial set. This is the complex modulo the degenerate subcomplex. Okay? So then there is a short exact sequence of complexes that degenerate into the full complex into the normalized complex. In each degree, by definition, this is a quotient. So this surjects in each degree. And it's short exact in each degree by construction. So there's a short exact sequence of complexes like this, and therefore a long exact sequence in homology. And we will check in exercises. It's not hard, but it takes a little bit of work. One checks that this degenerate complex of degenerate simplices is exact. So its homology is 0 in all degrees. So if you look at the long exact sequence, all of these terms will be 0. And we'll just have isomorphisms in the middle. So we'll get that homology of this big complex is isomorphic to homology of this reduced complex. And this reduced complex is much smaller, so this is very convenient to know. So put differently, this map, this quotient map, this quotient map is a quasi-isomorphism, and in fact a homotopy equivalence. So this is one typical example that involves things we've already seen. Here's another example which appears in definitions in algebraic topology. Suppose I have a topological space. And for some reason I don't understand, A in X is a traditional notation for the subspace. Then I can look at the singular chains in A. So that's built out of this kind of thing. I look at all maps from continuous maps from topological simplices into A. Those form the singular set of A. And then I perform this construction on that simplicial set. So because if I have a map from an n simplex into A I can compose with inclusion, I get a map from singular chains in A to singular chains in X. And this is free on those chains in each degree. So this is an inclusion. So two n simplices would become the same if and only if they were already equal, because this is an inclusion. So I get a subcomplex for every subspace. It's just the subcomplex of those chains which happen to live in the subspace. Let me finish this. And by definition, the relative chains are the quotient of this by this subcomplex. So by definition, there's a short exact sequence of complexes, chains in A, including into chains on X, and then the chains on X relative to A. This is the quotient complex. And then you get a long exact sequence in homology relating homology of A to homology of X to relative homology of X relative to A. And this long exact sequence is very important in computing homology of spaces. One reason it's so effective is that you can, in nice cases, relate this to homology of the space you get by collapsing A to a point. Okay. Now this is the relative one. And so on. Okay, so these are typical places in which this long exact sequence appears. We'll see lots more. So now we can go to the proof or construction. So I have to tell you how to construct these connecting maps, and I have to justify why it's exact. And we'll do this by the Snake Lemma. So the proof of the proposition uses the Snake Lemma. So to use the Snake Lemma, which I just rubbed off, remember we needed a right exact sequence on top, a left exact sequence on the bottom, and a map between them where everything commuted. So consider the following. So I wrote the maps alpha, beta, and gamma in the Snake Lemma. I wrote them vertically. Here, when I wrote my maps of short exact sequences, I wrote them horizontally, so I'm going to rotate it to make it look like it's in the Snake Lemma. So consider the following. In each degree, let's see, I can consider, yes. Maybe I don't need to rotate. Yeah, I don't think I need to rotate. So consider, in degree I, consider Li modulo the incoming differential. So those are the I boundaries. And similarly for m and n. Now, it's easy to check that this is exact. And down here, I will consider what do I want? Just a sec. Yes. Cycles. And this map is injective because it's the restriction of an injective map. And using that, you can check that this is left exact. And now if I take something in Li and I apply the what? Let's see. I apply the differential to something in Li, it lands in Li minus 1. If I apply the differential again, it goes to 0. So if I apply dIL here, I'll get a map here which lands in these I minus 1 cycles. And similarly here. This is Fi. This is induced by Gi. This is induced by Fi minus 1. And this is induced by G minus 1. Okay. So I claim it's easy to check this satisfies the hypotheses of the Snake Lemma. Everything commutes. Yes, right here. Thank you. Okay. So you check. This satisfies the hypotheses of the Snake Lemma. The squares commute. The top is right exact. The bottom is left exact. And now, what is the kernel of the vertical maps? The kernel is the I cycles modulo the boundaries. So that's just homology. We've already factored out the boundaries, but we don't see the cycles yet until we take the kernel of the vertical maps. And what are the co-kernels? Those are also homologies, because the images are the boundaries. So it'll be cycles modulo boundaries. So then the kernels of the vertical maps are the ith homologies. And the co-kernels are the I minus first homologies. So the Snake Lemma gives the desired sequence, gives the desired exact sequence. So you have to do this for each I and patch everything together. But what we've just constructed is this bit right here. This, the connecting map, and then the next two terms. It also gives you a formula for computing this connecting map. So I choose a cycle. I lift it from Ni to Mi. I apply the differential. And then I know that it's in the image of this, so I look at it modulo the boundaries here. Okay, so that's what we wanted to prove. Very good. And that We have 3 minutes left, so that's probably enough for today. Are there any questions about the long exact sequence, how we constructed it? No? Explain what? Why the kernel is the homology group. Right. So suppose I had an element here. I can think of it as an element of Li well-defined up to adding something that's a boundary. Apply this vertical map. Suppose it goes to 0. Well, it doesn't matter what I add on into the boundary. The boundary lies in the cycle, so di kills it. And so the condition that something be in the kernel here is exactly that. It's an element of Li, which applied to di gives 0, except it's only well-defined up to factoring out by the boundaries. So it's a cycle, but well-defined up to a boundary, and that's exactly homology. And similarly in each column. OK. Any other questions? Yeah. It requires more work. So I want to make this a kind of guided exercise because it's one of those things that's not so hard but takes many steps. It takes more work because this notation is very compact. What does it really mean? It means take a topological space, make a simplicial set out of it, then form this chain complex. Here, I could kind of do this in 2 steps. Maybe I have something which is already simplicial, but I kind of turn it into a topological space. There's something called geometric realization, and then I go back again. I'll get a different complex, but they'll be homotopy equivalent, and so I need to compare them. Okay, so see you in the seminar.